Hello, class. Welcome to week 3. We're going to today be talking about the golden ratio. But this week overall, we're going to be talking about generating functions, which are essentially a way to apply methods of calculus to solve or answer certain things about combinatorial problems. Uh, but because it's going to show up later when a bunch of things are going on, I wanted to first give you a brief introduction / refresher on the golden ratio. Just so that later when it pops up, we know the things about it that we want to know. Okay. So, noting that that's upside down, it's now right side up, very fancily. So what is the golden ratio? So the golden ratio you might think of as this sort of shape of rectangle that purportedly is the most beautiful shape of rectangle. At least according to the ancient Greeks, they believed so, and so you'll see all sorts of claims, like the Parthenon was built specifically to have this exact ratio, and you'll see people claim this about cereal boxes and cans and the Mona Lisa and nature and all sorts of things. Some of those turn out to be sort of completely true, some of them are completely bogus, and some of them are somewhere in between. But I want to figure out what is it that makes the golden ratio special? How do I separate the correct golden rectangle, which this obviously isn't because it's not even a rectangle, but pretend. How do I separate that one out from all the others? And so the basic idea is that this is the rectangle, where if you sort of look at the long side and you look at the short side, and you chop this so that this is now a square, and you look at this now, this sort of sub-rectangle here, the point here is that the little rectangle, the one that I got, again, by chopping off a square from the side of the big rectangle, this is similar to the big rectangle. Okay. Now, any rectangle where this is true is called a golden rectangle. And so the reason why it's called a ratio is that the only thing that's sort of invariant across all of these rectangles is the ratio of the long side to the short side. So by definition, phi, the golden ratio, is the ratio of the long side to the short side in a golden triangle, or sorry, in a golden rectangle. Okay. Now, because, as I said, in this definition, the small rectangle here is similar to the big one. That means that this is also itself a golden rectangle, the little one. And so, again, if you took and drew a square out of this, now this even littler rectangle would again be similar to this rectangle and the big one, and you could keep going like this. And so often you'll see people draw some sort of spiral through all of these things that's called an Archimedean spiral and blah, 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 blah. So those are all sorts of things that are going to show up. But I want to at least figure out how we can figure out what number this ratio is, so we can look at some of the strange properties of the number and things associated with it before we dive into other things. Okay, so I want to figure out what the golden ratio is. And the way I'm going to figure out what the golden ratio is by trying to find a golden rectangle. Okay. And the golden rectangle I'm going to try to find is going to be the one where the short side is 1, and so I'm going to call the long side x. Okay. And so I'm going to try and figure out what x is, and then the golden ratio will, as it happens, be x to 1. So I have to chop a square off this side. And then I have to look at the big rectangle and the little rectangle. So I need to label this length up here, and this length is definitely x minus 1. Because, well, if this is a square, that length is also 1, and so 1 and this length add up to x, so that's x minus 1. And so the claim that these two rectangles are similar is to say that for both of them, the ratio of the long side to the short side is equal. So that is to say x is to 1 as, and then now the long side is now this one for the little rectangle, so as 1 is to x minus 1. Okay, so that is our equation. Okay. I'll note, by the way, just as a short aside, different people define similarity differently, so I defined it as talking about the ratio inside the rectangle. That's because it's the thing that we're going to use over and over again. You might also prefer to define similarity by saying the long side of the big rectangle to the long side of the small rectangle is the same as the ratio of the little side of the big rectangle to the little side of the small rectangle. Conveniently, that gives you exactly the same identity, so even if you prefer it the other way, it's fine. Okay, so we're going to solve this equation for x, and then that's going to give us the golden ratio. So when I cross multiply here, I get x squared minus x equals 1. So that is x squared minus x minus 1 equals 0. And now you might try and factor this, but you'll be disappointed that it doesn't factor. So we're forced to resort to our friend the quadratic formula, which, remember, as always, goes to pop goes the weasel. So x equals opposite b plus or minus square root b squared minus 4 times ac all over 2a. So that is the way that if you want to get someone to remember the quadratic formula, or if you, like me, have the memory of a leaky sieve, you can remember it. So that gives you that this number is 1 plus or minus the square root of 1 minus 4 times minus 1, so that's 1 plus 4, which is 5 over 2. Okay, so that is two different numbers, but which two numbers, or which of these two numbers is right? Well, fortunately, I'm trying to find here, apologies, I'm getting the camera all set up and screwing it up. There we go, that's better. Fortunately, this thing I'm trying to find is a length, and one of these two numbers is negative. Namely, the square root of 5 is definitely more than 1, so 1 minus the square root of 5 is negative, so it's definitely not that one. So that means that the x I'm looking for is the positive one, and so in fact, the golden ratio, it is 1 plus the square root of 5 over 2. Okay, so that is the golden ratio. Now, if you're curious in terms of the grand scheme of sort of how messy and ugly numbers are, the golden ratio is itself irrational, because the square root of 5 is irrational, but it is algebraic, so it's not transcendental. Okay, and what does that mean? Well, it means it satisfies a polynomial with integer coefficients. Well, we kind of showed that here. So this number is uglier than 5, or 37/8, but it is not as ugly as something like pi or e, where you can't even talk about them with algebra. You need analysis to even define them. Okay. I want to note, while we're talking about the golden ratio, that there's some interesting things you might notice. So, namely, if I write down the decimal version of this, you'll get something that looks like 1.618 dot dot dot. Okay. I'm going to claim that this is really an equal sign because I put the dot dot dot. If you wanted to stop, you could put an approximately equals if you wanted. And then 1 over 5, if you work it out, it happens to be 0.618 dot dot dot. And that's kind of interesting. If you look at it, it seems like this probably isn't a coincidence? Question mark. We'll think about that in a second. But I want to point out something else, which is that if you actually look at the two solutions here, you have, on the one hand, 1 plus root 5 over 2 that is, well, that was literally what we picked, so that's the 1.618 number. If you pick 1 minus root 5 over 2, that is, well, if you work it out, it works out to be negative 0.618 something, something, something. Okay. So if you consider the idea that a ratio is really sort of a relationship between two things, the reciprocal of the ratio holds just as much meaning. In fact, it holds all the meaning of the original. So you can really sort of think of either of these as the golden ratio. This is the ratio of the big side to the small side of a golden rectangle. This is the ratio of the small side to the big side of a golden rectangle. And in fact, both of these are borne out over in the solutions of this particular quadratic that we looked at earlier. Okay, but I want to work out what on earth is going on with phi and 1 over phi. Why is it that seemingly the decimals here are the same? Because that's definitely not what you would expect, right? If you took a random, messy, irrational number and you took its reciprocal, you would not expect that exactly the same digits would follow the 0. And maybe it's perfectly fair for you to claim that I've only shown you 3 digits, and maybe this is some giant fluke coincidence. And in fact, actually, if I wrote out 5 more digits, it would turn out that, oh, hey, they're actually completely different. Okay. But let's try and figure out what's really going on here. Okay. So I'm going to try and frame as a conjecture the thing it is I'm trying to prove. So I think the way I would frame this as a conjecture, if I want to say that these two numbers have the same decimal, I would say that my conjecture here is that phi minus 1 over phi is exactly equal to 1. Okay. That would be my, my claim here. Now, in fact, actually, I can prove this conjecture for you. I can prove that this is not a coincidence. In fact, that's really a true fact about phi. Okay. And the way I'm going to do that is I'm going to start with the fact that I do know about phi. Namely, I know phi is a solution of this quadratic. Namely, we know, because we showed it earlier, that phi squared minus phi minus 1 is 0. And so, what does that tell me? Well, for reasons that will become clear in a second, I'm going to move this phi over to the other side. So phi squared minus 1 is the same thing as phi. Okay. But now you probably see what I'm going to do. I'm going to divide this equation through by phi, which conveniently is not 0 because it's 1.6 something. And so dividing through by phi, we get phi minus 1 over phi. It is, in fact, 1. Okay, and that actually proves that this number phi really has this weird property. And so if you think about the golden ratio, you're always going to come back to this polynomial in some fashion or another, and then the roots of this polynomial are sort of bizarrely, but you can make sense of it if you want, the golden ratio itself, and then the negative of the reciprocal of the golden ratio. Okay. And so these numbers are going to show up later, and I just sort of want you to recognize them when they appear. All right, but we'll wrap up there for now. In the next video, I'll tell you what on earth a generating function is, because I claimed this week I'm going to talk about generating functions. Until next time, be well.